Hi, so now with all these motivations in the previous video, I'm now ready to prove Stirling's formula for you. I introduced Stirling's formula in the previous video, and with drawing some graphs we concluded that it's kind of sensible to look at the approximation of log of n factorial by n plus 1/2 times log of n minus n. So we're going to start this proof. So we're going to proof of Stirling's formula now. And we're going to start this proof by looking at this dn exactly. Okay, so proof. We are looking at this dn log of n factorial minus n plus half log of n minus n. And we're going to show 2 points. Step 1, we're going to show that dn is monotone decreasing. Which immediately implies that the limit of dn exists, and I'm going to call this d. Okay, so we're going to show that there is a limit. And the other thing is, so it's monotone and therefore there is a limit. The other thing is that for every n, we are going to have that, of course, dn is larger than d. That's no surprise because it's decreasing, but not by too much. Actually, it's never larger than d plus 1 over 12n. Okay, that's going to be the second step of the proof. And the first thing I want to mention now is that once we know these two, then actually Stirling's formula follows. Okay, so why is that? So then if I look at exponential of d, it's going to be smaller than exponential of dn. And what is exponential of dn? What is exponential of dn? So that's what dn is. Take an exponential of that. That gives me exponential of the log, which is just whatever I see inside, so that's an n factorial. Exponential of the parenthesis, except it's in the denominator because of this minus sign. So you have to take an exponential of all of this, and that's giving me n to the n plus 1/2 for the log, and it's also giving me an e to the minus n for this bit. Okay, and on the right hand side it's going to be smaller than exponential of d plus 1 over 12n. Okay, and if I now divide by e to the d, that gives me n factorial over n to the n e to the minus n. I can just bring it underneath here, and then I can have a root n, and then I have this constant e to the d, and that's smaller than e to the 1 over 12n. And the last thing I need to do now is to compare this with the statement. The statement is, the Stirling's formula is that 1 is bounding n to the n factorial over n to the n over exponential of n square root of n times a constant. And that constant e to the d will have to match up with the square root of 2 pi later. So this proof will not show what the value of this constant is, that comes later, but there's going to be a constant with which it works, and the right hand side I have the same bound. Okay, so the first step of the proof was to realize that if I prove that dn is monotone decreasing, and if I prove that dn is never larger than this limit plus 1 over 12n, then the statement follows. So Stirling's formula, except for the value of the constant, Stirling's formula follows. Okay, so what I need to do now is prove 1 and 2. So proof of 1 and 2. Okay, to this order I'm going to concentrate again on this quantity dn, and I'm going to see how that quantity changes. In fact, I want to see what dn minus dn plus 1 is. It's kind of the decrement, if you want. It would be an increment if it would be dn plus 1 minus dn. This you can call decrement. Okay, so let's plug in what that is. The first thing to notice is, so here is dn, is that I'm going to have a log of n plus 1 factorial minus a log of n factorial, and factorials are products. The log of them is a sum, so that gives me a log of n plus 1 with a minus sign. That's coming from the log of n factorials when I take it at n plus 1 and subtract it at n. Okay, so this is log of n plus 1 factorial with a minus and the plus log of n factorial. The next thing to notice is that I am going to have a log with a minus. I'm having this term n plus 1 half log of n. That's just coming from dn here. Then I have with a minus and another minus the same term at n plus 1 log of n plus 1. Okay, so these terms come from this with the minus at n plus 1 and with the plus at n. And then I have a total of plus n minus n plus 1. So together the last term is just giving me a 1. So this term n at n plus 1 with a negative sign minus n at n with a positive sign is giving me this minus 1. Alright. The next step is to cancel out the log of n plus 1 with one of these logs of n plus 1. So this thing cancels out with one of those and leaves me with 1/2 of that only. And that's nice because that will mean that I can factor out an n plus 1/2. So n plus 1/2. And I have a log of n with a minus and a log of n plus 1 with a plus. So I'm going to start with the log of n plus 1. And if I subtract the log, that's the same as dividing with stuff inside the log. And I get to this expression here. And now I'm going to do something very strange. I'm going to make things more complicated. I'm going to make things more complicated. I'm going to write n plus 1 over n in a very funny form. It's 1 over 2n plus 1 over 1 plus 1 over 2n plus 1 over 1 minus 1 over 2n plus 1. That's inside my log. So if you want to check that this is true, you just multiply top and bottom with 2n plus 1. That gives 2n plus 2 on top, and it gives 2n on the bottom. Cancelling with the 2, you get back exactly n plus 1 over n. It's not entirely clear why I did that, as long as one substitutes, unless one substitutes t equals to 1 over 2n plus 1, which is small. N will go to infinity, of course, and or at least that's how we should think about it. And this is going to be small. And if I do the reciprocal of that, 1 over t is 2n plus 1, of course. And 2n plus 1 is exactly the half of what I see here. Exactly twice of what I see here. So this thing is half of 1 over t. And then the log will be nice because it's 1 plus t over 1 minus t inside. And I have this formula here, which I could further write as 1 over 2t log of 1 plus t minus log of 1 minus t minus 1. Okay, just a bit of algebra. Okay, so log of 1 minus t was featured in a previous video. Log of 1 minus t was done in the law of rare events video, log of 1 minus x is minus the sum of x to the m over m. And that's what I'm going to use for 1 minus t and also for 1 plus t. Okay? So the next step is to plug in the Taylor series, which we found before, for the log there. Oops. So this is going to be 1 over 2t, and for log of 1 minus t, I can just plug in. For log of 1 minus t, I can just plug in minus the sum of x to the m over m, except I'm going to use k. So minus the sum from 1 through infinity of t to the k over k. This thing here was, according to the law of rare events video, log of 1 minus t. And then I'm going to do the same there, except I need to swap t to minus t. So this is going to be the minus sum from 1 through infinity minus 1 to the k, t to the k over k, and a minus 1 at the end. So minus t can also be written as minus 1 times t, and that's what happened here. Okay, now the next step is to factor out whatever we can in this sum. So 1 over t, 2t actually. Let's put in a sum for 1 through infinity. These two minuses cancel out, so I'm going to start with the t to the k over k once, and then I have a minus negative 1 to the k. So another parenthesis here, minus 1. All right. So that's how far I got now. And then notice that when k is 0, then minus 1 to the 0 is 1, 1 minus 1 is 0. So when k is 0, I don't have any contribution. Okay, k is never 0. But when k is 2, minus 1 to the 2 is again 1, 1 minus 1 is 0. And when k is 4, and when k is any even number, then this minus 1 to the k is becoming 1. 1 minus 1 becomes 0, so I don't have any even contribution here. All the even k's just disappear. This is going to be 0 if k is even, and it's going to be 2 if k is odd. Because for k odd, like k equals to 1 for example, this is 1 minus negative 1, which is 2. So I only need to look at k odd, and in that case these two will cancel out that 2. So it's 1 over t. I have to do a summation for odd numbers, and I'm going to do that in the form of 2l plus 1. So l is going to go from 0 to infinity. And I'm going to replace these odd k's by 2l plus 1 when l goes from 0 to infinity, so k will go from 1 to infinity through the odd numbers. In that case, all of this parenthesis is just 2, which I cancel out with that 2, so I don't have to deal with that anymore. All I have left is t to the k, which is now 2l plus 1, over k, which is 2l plus 1, and the minus 1 at the end. Okay, and the next step is to say that L equals to 0 exactly gives me t to the first power over 1. Together with that t, L equals to 0 gives me a 1 for this sum, which exactly cancels out that 1. So I'm going to start L from 1 to infinity, and that will get rid of, actually, well, let me keep this 1 over t in front. that will get rid of the -1 here. So I cancelled out the -1 by starting my summation from 1 only, because L equals to 0 just cancels out with that -1. Okay. Now, an interesting feature of this is that this is actually strictly positive. T is strictly positive, L is, everything is positive here. This is positive, and that immediately shows number 1. dn minus dn plus 1 is positive. So that means that dn is monotone decreasing, is strictly decreasing actually. Okay, so step 1 is done. Property 1 is done. This thing is monotone decreasing, and therefore it has a limit, which we denoted by d. Step 2, in fact, I can proceed with this calculation. And say that this is smaller than 1 over t sum from 1 to infinity t to the 2l plus 1 over 3. And the reason is that when L equals to 1, then this is a 3. When L is larger than 1, then this is larger than 3. So it's smaller than if I just replace that by 3. And this is something easy to sum up, because it's simply a geometric sum of t to the 2l from L goes from 1 to infinity. It's the L's power of t square, and t is smaller than 1. So I can sum this up easily. The first term is t to the square, and the common ratio is t to the square, which now I can write back from my previous substitution. My previous substitution was that t, the reciprocal of t is 2n plus 1, or t is 1 over 2n plus 1. So I'm going to plug this back in. T square is 1 over 2n plus 1 squared. I have a 3 here, and I have a 1 minus 1 over 2n plus 1 squared. So let's multiply both numerator and denominator with 2n plus 1 squared, and that gives me 1 over 3 times 2n plus 1 squared minus 1. Okay? Which I can further simplify a little bit by breaking up the square. Breaking up the square gives me a 4n squared, which is together 12n squared, and it gives me a 4n, which together with the 3 is a 12n, and there is a 1 square here which cancels with that one, so I don't even need to write that down. So all I have left is 1 over 12n squared plus n. And now comes something very nice and very useful. This I can write as 1 over 12 times 1 over n minus 1 over 12 times 1 over n plus 1. The reason is that the common denominator would be exactly n times n plus 1, or if you want n squared plus n, and I have n plus 1 of that minus n of that. That's just one of them. So I can write this in this very nice way. So what did I get? I'm still calculating dn minus dn plus 1. I'm still doing dn minus dn plus 1. And actually upper bound on that. So what I got so far is that dn minus dn plus 1 has an upper bound on it in the form of 1 over 12n minus 1 over 12n plus 1. This is the summary of the previous few pages, right? 1 over 12n minus 1 over 12n plus 1 is an upper bound on dn minus dn plus 1. All right? which I can rearrange in the following way. dn minus 1 over 12n is smaller than dn plus 1 minus 1 over 12n plus 1. Trivial. And that shows that dn minus 1 over 12n as a sequence in n is increasing. If I increase n by 1, then I get something larger. Okay, so this thing is increasing. And therefore comes the last line of the proof. So therefore, I can now do the following. Start dn minus d. Remember that d is the limit. D is the limit of the dn, which I know exists because I already proved it's decreasing. dn itself is decreasing, so it will have a limit. Let me put that in. dn minus limit as m goes to infinity of dm. Now, m is the variable I take limit in, and for that purpose dn is a constant, which means I can pass the limit through the dn. It doesn't depend on m. Okay? And that is the same as the limit as m goes to infinity, so I want to make use of this increasing property here. And for that reason, I'm gonna add in, actually subtract in 1 over 12n from dn, and I'm gonna also subtract 1 over 12m from dm, but of course it's not equal now because I subtracted in artificially 1 over 12m, so I have to add that back, and I added 1 over 12m, so I have to subtract this, so I have that. Okay, and now comes the point about dm being increasing. This thing, dm minus 1 over 12m, is larger than dn minus 1 over 12n for large m, and that's because dn minus 1 over 12n is increasing. So as soon as m exceeds n, this will be larger than the same quantity with n, which means that those two terms together are going to be negative, and therefore this whole business is less than, for large m, it's going to be less than the limit as m goes to infinity of the terms without these two. So these two together are negative. I forget them, then I'm making the whole thing larger. 1 over 12n minus 1 over 12m. This is easy to take a limit of. It's 1 over 12m, and at this moment I'm done with property 2, because property 2 exactly told me that I need to prove dn minus d less than 1 over 12n, and that's exactly what happened here. So now property 2 is proved, property 1 is proved. These together imply that the statement is true. That's what we started with before, and now Stirling's formula is completely proved. So that's the end of this story here.